when we first talked about accumulation functions, we were accumulating area, right? Using some sort of definite integral. We defined a function based on a definite integral. Well, we're going to do the same kind of thing, but instead of accumulating area, we're going to accumulate arc length. And here's what it looks like. So we're going to define a function f, no, s, there we go, which is based on the length of a function, which is a smooth curve, called f on a closed interval from a to b. Okay, all right, so notice that this looks very, very similar to what we did with our accumulation functions. And notice the change in variable that's happening here. So the variable for our function, s of x, x is the upper limit of our definite integral, but inside the integrand here, we have a t because we don't want to get confused with those different variables here. So this is called an arc length function. So for example, if this was a 1 down here, just as an example, and I put a 2, then S of 2 is finding the arc length from 1 to 2. S of 4 would find the arc length from 1 to 4, and then so on. I'm going to plot this thing as a graph. Here, let's take a look at an example of this thing. Example 8, define an arc length function S for f of x is equal to x squared minus 1/8 natural log of x, where 1 comma 1 is the initial point. So here is the graphs of these things. Analyze the graph of s of x. Where is it increasing, decreasing? Does it have any points of inflection? So I already threw some graph pictures down for you. So here is the original function, but we are just basically from 1 and on, we're defining this arc length function. We can go to the left, and when we do go to the left, that means that our arc length is just going to be, I'm taking away some distance, so it's going to be negative, which is why we have this portion that's down here. Now, as far as this goes, it says, where is it increasing? I can see from the graph that it's always going upward, so it's always increasing. But I'm going to show that with calculus. How do I find increasing and decreasing with calculus? Remember, it's been ages. We do that with the derivative. We see if it's positive or negative. This one should turn out to be positive. Let's take a look at that graph, right? It should always be positive. Does it have any points of inflection? Well, what do you think? Is there a change in concavity? This looks like it's down here. This looks like it's up here. So it looks like there could be a point of inflection there. How do I find points of inflection? I find that's from the second derivative. Okay, so let's put all of these pieces together. It's going to link together stuff that we've done in this lesson with stuff that we've done ages ago with increasing, decreasing, and points of inflection. So let me just write our function down again, just out of convenience. F of x is equal to something, 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 x. It says f of x? Okay, yeah. X squared minus 1/8 natural log of x. All right, and we want to define an arc length function for this, so we need its derivative. F prime of x is going to be equal to 2x minus 1/8 is going to stay, and the derivative of natural log is 1 over x. That becomes 1 over 8x, right? Right. All right. And then we are using the point 1 comma 1. So 1 here, this x value of 1 is going to be the lower bound of our arc length function. So s of x is equal to the definite integral from 1 to x. X is the variable for our function, so I have to make sure I don't use x inside of the integrand. Square root of 1 plus parentheses 2t, or choose your favorite variable that's not x, minus 1 over 8x squared dt, since I used a t in here. Oh, I put an x there, and I switched them up. Confused. Yep. Okay. So there you go. There's your arc length function. But I think that we can resolve this a little bit. We can maybe do a little bit of calculus and clean it up. Let's square this binomial out. I'd have 4t squared, and then multiplying these two things together, a 2t times a negative 1 over 8t. T's cancel, and then I think I get negative 1/4 from that. Negative 1/4, but I have to double it, negative 1/2, and then plus 1 over 64, that's a 4, t squared, dt. And then look what happens. Same thing is going to happen on this example that happened on, I think it's like the first one. This 1 and this negative half going to combine up to make a positive 1/2, which is going to be identical to squaring out this thing, only with a positive instead of a negative. See how convenient it is? 1x square root of 4t squared plus 1/2 plus 1 over 64t squared dt. And then, as I said, this is a perfect square. It's going to factor exactly like this with a little plus sign in the middle because we switched the sign there. Equals, hey, this is supposed to be an integral sign. Come on. Square root of 2t plus 1 over 8t quantity squared dt. And these square and the square root are going to cancel each other out to give me just the integral from 1 to x of 2t. I was about to put an x again. Plus 1 over 8t. I'm going to rewrite this one, though. 1/8 t to the negative 1 dt. Because now I can term by term take the antiderivative. And that's going to be a 2t squared over 2, so just t squared. Plus, let's see, 1/8, actually minus, t to the, oh, no, that's not the way that works. Actually, I did need to keep that. That doesn't work that way for the power rule. 1 over t is natural log. Plus, and I should have known that anyway. You know why? Because this does some crazy business where it goes back to the original function with this like change in sign. Why? Does it always happen? I'm not gonna, I have no idea. I don't have enough, inductive reasoning experience in order to be able to tell. We've only looked at a couple of examples where it's done that. From 1 to x. All right, throw our x in here, throw our 1 in here. We have an x squared plus 1 over 8 natural log of x minus, now throw our 1 in here, 1 squared plus 1/8 natural log of 1. Natural log of 1, that's 0, that's going to go away. That's just a 1. I'll distribute the 1, and then we have our final arc length equation, which goes s of x is equal to x squared plus 1/8 natural log of x, all of that, minus 1. Ta-da! Look at that function. It's so close to our original one. Has a plus sign inside of here instead of a minus, and then we subtract 1 from the end of it. Just strange. Absolutely bizarre. Okay, and then let's add an extra page because we still need to do the increasing, decreasing, and concavity bit. So to find increasing and decreasing, we're going to take the derivative. S prime of x is equal to 2x plus 1 over 8x, and then the negative 1 goes away. So, as far as all this goes, I could have easily gotten this by just taking the derivative of, where is it? After we cancel, like we simplified it right here. Here, let me actually put this the way it's supposed to go. 1 over 8d. There we go. Right, when we take the derivative of a definite, of a function defined on a definite integral, you just get this change of variable, right? And it's exactly what we just got there. Yeah, okay. So we need to find a critical number so we can find where it might change, increasing or decreasing or whatever. So set it equal to 0. Let's say I will subtract over the 2x. How about that? Negative 2x. And then maybe multiply the x over, divide by negative 2. I would have negative 1/16 equals x squared. And then I can pretty much stop there because it's always positive. That's not going to happen. Here, let me just cross this thing out. This thing is always positive. Greater than 0 for all numbers? No matter, no, not for all, for x greater than 0. Yeah, for x greater than 0. Which means, since, say, s prime of x is greater than 0 for x is greater than 0, then s of x is increasing. And you can see that I have myself an asymptote right there, so I'm not going to use that. I'm going to go from 0 to in like that. Yeah. On 4, whatever. Okay, all right then. And now we've answered the first part of the question. Actually, the second part, because this is a 3-part question. Now we need to find the second derivative here. So s double prime of x is equal to just 2. This is 1/8 x to the negative 1 power. So negative 1/8 x squared. Yes, okay. So just like we did before, we need to find where this is equal to 0. Supercrits. Okay, this time I'm going to add over the 1/8x squared. So 2 is equal to 1/8x squared. Did I do that one right? I'm just wondering. Yeah, still 2, 2 is 8. Yeah, okay. Anyway, let's see. I will multiply the x squared over, divide it by 2. X squared is equal to 1/16. X is equal to plus or minus 1/4. The negative doesn't make any sense, just a positive 1/4. So we have a potential. Remember this, just because we get one doesn't mean that it's necessarily a point of inflection. We need to do a test for concavity. This is not second derivative test. Remember, second derivative test for relative mins and max. This is a test for concavity. But it looks like the first derivative test, or the test for increasing and decreasing, right? We need some intervals. And we're going to go from 0, open, to 1/4, and then from 1/4 to infinity. Choose an x value. How about an 1/8 here? And then over here, we'll choose just 1. And we need to plug these into the second derivative in order to tell something about the original function. We just need plus and minus, that's it. So if I stick in the 1/8, we're plugging it in right over here. Let's see, I would have, maybe change this to rate. Okay, I'm going to have 2 minus 1/8 times, this is 1/8. 1/8 squared is 1/64. So that is 2 minus 1/8, which brings that 8 up to the top. So it's 2 minus 8. So it's definitely a negative number. So this is a concave down kind of shape. If I plug in 1/4, no, not 1/4, 1. If I plug in 1, that just makes it 2 minus an eighth, which is definitely positive, and it is concave up. All right, yeah, so we definitely have a point of inflection here. We have a concave down shape and then a concave up. So as far as justification, remember on the AP exam, it would go sort of like this, that S of x has a point of inflection at x is equal to 1/4, because s double prime of x changes signs. And I don't really need to say that it goes from negative to positive. We just need to see that it changes signs at x is equal to 1/4, right? There you go. All right, so that concludes that problem and the entire lesson on arc length. As you can see, finding the arc length of a smooth curve, you need the function and you need its derivative inside. Is basically using like the distance formula and stuff like that. And once again, we have ourselves a homework supplement that has a free response question, sort of like our cake question without the cake. Anyway, it has some sort of arc length built into it.